So your output resistance of your transistor, which is inside the transistor, right, is parallel to your output discrete component RC, right? Look, one node is common and another node, obviously through emitter but grounded, so seems to be common, right? So okay, now hybrid pi model based AC equivalent circuit is completed partially because you have not yet found the values of the new parameters coming in this model, right? So let's find it. Gm is equal to IC by VT. IC you have found, VT is given, put it to get 230 millimho. Mho is the invert of the ohm, or you can write ampere upon volt, right? R pi is Vt by Ib or beta by Gm. You can take any relation, right? So it comes out to be 1.3 kilo ohm. R naught is Va plus Vcq by Icq. You have your Q point. You already have given a value of Va. When we got 18.8 kilo ohm. It usually have high values, right? So now we have drawn the AC equivalent circuit. Part of C part is done of the given question. Now for the D part, the last part, the voltage gain we have to express it in the form of equation and then putting the values in the expression to find the exact numerical value of the voltage gain, right? So we have this model based equivalent AC circuit, right? Only AC and right. So we have to find now the V pi, that how much voltage from this input signal is developing across V pi, and then we can go to this output side. So the beauty of this model is once you have drawn this model, now you can use this input part and work out separately to find V pi, IB if necessary, and so on, and then just use this value here and solve this part separately, right? So for V pi voltage developing across this, let's see what is in this circuit. What is the resistance feel is feeling by this supply when going into the transistor. So your RB looking into the base, the resistance looking into the base by the current coming from Vi is RB. So it's only R pi. You are not having other resistance, right? So RB is equal to R pi, right? And this is the total input resistance seen by this input, right? Because it will through the current according to the overall resistance field here, right? So it is feeling an input resistance here, which is the combination of these two things, right? So these two resistances are coming in parallel, right? So RB parallel to R pi, and when we find this, we got this value. We already have this value, right? R pi. Also, this collector current, the current depending on this voltage, once you have found this, you can multiply it with the GM. You can get your collector current, right? But this collector current is flowing from which resistances? It's actually flowing from the combination of all the resistances here. So you can see R0 and RC are parallel. So basically your, if you want to name it with the terminal, you actually named it V0 is R0, R out, right? So basically you actually have an output resistance for this current source, right, to be used as an output port, right? For your stage you have your output here, so it means whatever resistance is coming in this terminal is the output resistance of your stage, right? So this is the output resistance, which is the parallel combination of these two things, right? Is R0 parallel to RC, right? And we can find its value as well, 1.3 kilo ohm. You can see it is nearly the value of this RC, because R naught has much higher value than RC, right? So you have a slight change in your output resistance as compared to the RC. So if you would have neglected the early effect, you would not have taken this R naught, your R naught, this small R naught, your output resistance looking into the output terminal would be equal to RC and having no much difference. But if you want the exact calculation, you have to consider the early effect. And if you are asked to consider early effect, you have to consider the early effect, right? And use this small R naught, right? So we have found the input resistance, so simple. We have found the output resistance, so simple. Now we can write the equation of the output voltages, right? So you can see this current, obviously depending on the value here, right? Let's just find this value, right? So your V pi is equal to Vi here only in this circuit, right? Because there is no resistance in series with this voltage source, right? So that's why this whole voltage source is in parallel with RB and in parallel with R pi, right? So your V pi is equal to Vi. Otherwise, if you would be having a R signal here in series with the source, then part of this voltage would be developing across R signal and will not be developing across here, right? And the part of signal which is appearing here would be used as V pi, right? So we have to just use our previous calculations of loops and Ohm's law, Kirchhoff's voltage law, Kirchhoff's current law to find this V pi out of this Vi, right? So currently it is equal to Vi, but it would not be the case every time. So V pi is equal to V in, right? How about V out? So now whatever V in you apply, it would be your V pi, and your Q point gives already have given you the value of Gm, then that V pi multiplied by Gm is your current, right? Then how about output voltage? I'm interested in finding the value of output voltage. So your output voltage would be equal to this current multiplied by the resistances it is passing by, right? So you can see this current is coming from where? From here, right? From here and from the combination of these two resistances, right? So it's actually coming from the ground, from the parallel combination of these two resistances, and then passing by here into the transistor, right? So it means your V out is equal to this current GMV pi times R naught, total output resistance, right? GMV pi times R naught. But this R naught, think of these two resistances as a single resistance placed here having value R naught, right? You have already found. This is the current entering terminal and this is the current leaving terminal of this component, right? And you want to write the equation of this terminal, which is the current leaving terminal. So it means for current leaving terminal, you should be having a negative sign for Ohm's law, right? So it is equal to V naught is equal to minus Gm V by R naught, right? So please recall that for common emitter configuration, you have observed the output voltage by applying an input voltage, right? And you have seen that the output voltage is totally 180-degree out of phase of the input signal. So your mathematical relation is representing this thing with this minus sign, right? So this is a perfect equation for the output of this transistor, right? So how about the gain? We know that the gain is equal to the output divided by the input. So you are interested in finding the output, the voltage gain. Voltage gain, so it would be the output voltage divided by input voltage. If you would be interested in current gain, output current divided by input current. Power gain, output power divided by input power. Okay, so we can divide this equation with your input voltage, right? Your Vn is V pi, right? Your Vn is V pi. So V out by V in, then V pi cancel out, and then we can get minus GM R naught. Minus GM R naught because V pi divided by V pi is cancelled out, right? So you might be having a question when you read this part of the question before attempting it, right? That we have to find the voltage gain and writing the expression of the voltage gain and find the numerical value of the voltage gain, and we not have yet given a value of Vi. Then how could we find the value of the gain? Please note it down and look here. You don't need any input voltage to find the gain. Yes, of course, to find the output for an input, you need an input to find the response of your system as output, right? Otherwise, for gain, that this circuit will give you this much gain at the output for an input, right? So it means you have GM already, you have R naught already. Put it down, and you can see your gain is nearly 30. So it means if you want to apply a signal of 1 millivolt, you will get at the output how much? 29.9 millivolt, right? For example, if we want to apply 2 millivolt, then it would be equal to 598 milliohm, right? So let's simulate it and check the validity of our analysis. This is the circuit we have drawn, right? R1, R2, RC is 1.4, and you have a 16 volt VCC, right? An input AC signal to be amplified is injected through a capacitor, a coupling capacitor, and output need to be taken out of this capacitor, right? So currently I have eliminated the AC source, right? Because I want to see the DC biasing. So from emitter to base, emitter already grounded, but I still make a reference so that you will remember to see the VBE. So it's almost 0.7 volts, right? What we have asked for, right? And your VCE is 7.85 watt was the value, right? It's nearly that, right? And how about the current is 5 was 5.75, right? It's 5.78, right? So it's okay. So your transistor is biased perfectly, right? So how about the AC signal? So we are applying 2 millivolts, 1 kilohertz signal, and let's see what is going on. This is the collector current. We actually want to see the, this is the total voltage. Look, we had DC VCE 7.85 theoretically and 7.89 practically here, in simulation, right? So your AC is fluctuating about that DC value, right? So if you, because at the output you want only AC output, so when you take the output from after this capacitor, your DC will not be available here. So your AC fluctuates but about zero. So you can see DC AC is fluctuating about zero. So you are only having AC collector to emitter voltage here, right? So this is your output. So you can see 5.98, what is the value? It's 5.44, right? It's just because of some mismatch of the parameter of this transistor and the one we have taken, right? So it's working perfectly. Now what you have to do is to neatly write down this example, this solved example into your notebook and simulate it to verify similarly as we did here, right? And also you have to solve this problem, right? Its solution is available as similar to problem 5.60 of the solution manual of edition, previous edition of Cedra Smith given to you in the soft form, right? Thank you very much.